So let's make our next laboratory work. And today's laboratory work is some crossover between bands. We have plotted band structure last term, and we have plotted those, and then we combine them to show some features like which bands was created for which orbitals, for which electrons, and so on. And now we use some crossover. So we will combine density of states and combine band structure. And it's so-called Carrizov DOS, or it's also called fat bands. It's like some what's fat bands? Key resolved DOS. Key resolved means that we plot. Okay, I will explain this this later. So just few words about density of states. What is it? It's some reminder. It's slide from previous term that we have our reciprocal space. So we have a real space, and then we create reciprocal space. Why do we need it? Because it's easy to create energies. Because in energies, you see p squared divided by 2m, and p is h Dirac constant on k. K is a wave vector. So wave vector, what is it? It's 2p divided by lambda. Lambda is some it can be some wave, it can be some dimensional like lattice vector. So it's easier to calculate energy in reciprocal space. That's why we use reciprocal space. And this reciprocal space we can divide. We can say that here somewhere are some places where electrons localized. And electrons, according to Pauli exclusion principle, they can be in the same state. Only two electrons with different spins. And according to Heisenberg uncertainty principle, we can say that this electron will be in some range of energies. We can say that it will have this energy, and we can say that it's this energy and no other energy. We can say only interval, so it can have some interval. And in this reciprocal space, electron will sit in some volume to p divided by L. So this volume, it goes from uncertainty principle, and we can say that it sits in some small volume in this energy space, in this reciprocal space. We fill the space with these volumes. It shows like some cubes just for simplicity, and we say that in every of these cubes, in every this site, we call it sites, can be seated two electrons, one with two spins. So we fill it with sites. In each site can be two electrons, and then we can calculate density of the sites per some energy. So it's very easy. What is the number of sites? We should take all the space in this reciprocal space. So it's like sphere with some radius k. Then we will call it Fermi vector. So what's its volume? 4/3 pk in the power of 3. We divide it in the site volume, and we get number of states. Then we can calculate density of states. We just shoot this number of states divided by some energy, by some energy interval, and we see how many of the sites, of these energy sites, will be per some small energy interval. So usually, you remember from last term that we got not too high number of states. It can be 0, 0, 0, 1 or 4. it's just tiny part. It can be just tiny part of site for some energy difference intervals. For some energy difference, we can have 80 or 100 sites. So it means the more sites we have, the longer this band in band structure diagram. And how we can connect them. So I also have showed this slide. I don't know if you read this book. I have sent it to our Telegram channel. So we can calculate the number of states, those density of states per year. So on dA, dA is some interval from E to E plus dA. So we have some number of states in this interval, DOS E, dE. And then we have some band structure and some DOS distribution, this DOS plot. And it's very easy to combine them. If we have this flat bands like this, we have a lot of density of states. Because here in this, in some intervals, we will have a lot of that small sites. That's why here we will see some peak. Then if if it goes down or up with rather high angle, we will see the smallest amount of doses. So it's rather simple. Flat band gives us high peaks and I don't know this word in English. Not flat, but curved. Maybe curved.
With a high slope.
Yes, high slopes with high tangents. It has very low number of states. Just some example also from the book how we can combine this things. I think maybe you I showed it for first time when we touched the density of states, and I think maybe now when you have some experience with these calculations, you can feel this this picture in different ways. So you can maybe you have a deeper understanding how it works, because we have calculated a lot of such band structures and a lot of doses, and we have combined them and we have seen what happened here. And you see that, for example, this peaks it created by two bands. This DOS created by two bands. This D band, it is rather flat, so it gives us high amount of states, and then we have very long band, very wide band, and it gives very slow amount of very low amount of those. Maybe totally this band give us higher amount of doses, but they are extended. That's why we don't see high peaks. And also we used some such thing which called partial density of states. So it means that we can take some atom, or we can have some orbitals and see how many states it creates. For example, titanium selene. So we made these calculations in titanium selene 2 example. So we can see how many, we can see total doses, and then we can see how many doses creates titanium, for example, 3D orbitals. And we see that 3D orbitals, titanium 3D orbitals, they give the biggest amount of states. So it's here in some interval from 0 to 2, and we can see here. So we can say that these orbitals, they created by titanium 3D orbitals, these bands. So if but these bands, they mostly created by selenium 4p. You see, from -4 to 0, it dominates. This 4p selenium dominates. So we can say that here valence bands created by selenium 4p, and then when we have some conductivity here in this material, electrons goes from here to conduction band, and conduction band it's mostly 3D. That's the information we can easily get from this thing, and we can go even further. So it's from our paper. This is what I call fat bands, this thing. And here you see just ordinary bands for titanium S to titanium selenium 2. We had to compare those two materials. And you see this, and here you see that some bands are really fat, they are really wide, and some bands are very tiny, and we almost don't see it. What does it mean? It means that these electrons, it means that, for example, here localized very high amount of doses. And for example, here we have not so high amount of doses. And it's very easily connected to what I said previously. So this is how we call it, curved, or so this is not flat band. Yeah, you see it goes up. And I have told that doses here that we don't have a lot of doses here on such bands. But this band, it is rather flat, and that's why we will have a lot of doses. So electrons will be sitting mostly here, or maybe here. We see we also have some bright color for it. And if you remember Fermi surface for titanium selenium 2, we had some cylinder in the center, and this is what it means. It means that these electrons, they are sitting in that cylinder. We can.
So I guess such configurations with a higher amount of concentration of electrons near the Fermi level, they favor some structures like superconductivity, ferromagnetism, and other.
Probably yes. So it's one of predictor. If we have some flat bands, this is not so flat band. You see, it's not too long, and it's not so flat as we want. So if we have really flat band very close to Fermi level, then we can say that maybe this material have some superconductivity properties, because we'll have a lot of states in one band, and it's very easy to electrons to move through the band.
By the way, I think the antonym for flat in this case would be steep, right?
Steep.
Yeah.
Skip. Steep. Okay, so this is steep bands, and we see not so high amount of doses here. Yeah, but here you see it's some one or two. So it's some point where two bands goes together, and we see higher amount of doses here. So it's very interesting. It's very advanced instrument to analyze the electronic structure of our material. And now I can propose you to calculate it. So today we will move, and also it will be some training for you in working with our computational cluster. And today we will go on this. So we will start from relaxations with this material magnesium B2, and then we will go to calculating K-resolved dose. So, and you see that we had two tracks. We have track for band structure calculation, and we also had track for non-self-considered calculations, which leads to partial doses. And partial doses we created on the basis of non-self-considered calculations. These band structure calculations is also not non-self-considered calculations, but what's the difference? In this case, we calculate all billion zones, but in this case, we calculate some particular high symmetry path. And as we want to combine DOS and bands, we should combine this project WFC, so it's projected wave functions. It was here when we created partial DOSes. We used this model, projected WFC. But now we will use it here. So we will calculate band structure first, and then on basis of this data, on basis of these wave functions, we will calculate DOSes. So that's the connection. So here we can just get the common DOSes. It's just common DOSes. But here we can connect bands and DOSes. And I propose some of you who want to start from this relaxation to fill this material, to fill this file from lab, from the folder I gave you.
I think we can probably start from the potentials.
You can try to speak louder.
Okay, I think we can start from downloading pseudo potentials.
Yeah,
That's pseudo potential for B. What should we use? PBSO?
PBSO, yes. PBSO, it's slightly better than PBE because it made specially for soils, and PBE is rather good for some molecules. The difference should not be too high. They say, the guys who created this PBSO, they say that it's more stable, this pseudo potential, so you will not have, you will have a lower number of some errors by using it. Yeah, you choose for boron and for magnesium PBSO pseudo potentials.
Yeah. So, what's SPML?
It means what orbitals we use. So it's okay. So
okay,
now we use color relativistic. In one of next laboratories, we will use full relativistic to calculate spin orbital interactions.
So, okay, what do we have here?
No, rel is not our choice. Rel is full relativistic.
I have to check what do we have here. So that's okay.
This is okay.
Yes.
The first is okay.
So we always preferably produce this potential in case of heavy elements or the
It means it depends. So the question is that should we use full relativistic for heavy elements? Probably if you plan to make some quick research, some quick calculation, and to check basic things like DOS band structure, it will be okay. If you want to see some tiny effects, like for example, if you will use a spin orbital coupling in addition to full relativistic, you can see that some bands they slightly split it. It means the effect of spin orbital coupling. You should spend a lot of computational time to get this. And in most cases, it's not so different. It's not so important. So maybe it's important when you make really super deep research, but in most cases, when you should get some band structure, the common band structure will be okay. So you opened, yes, magnesium B2.
Magnesium B2.
You can rotate it. You can rotate it, and we can discuss some of its structural things. You see, can you rotate it?
Like this?
No, but in 90 degrees.
This?
Yes. You see that we have two. We have some layers of boron, and we have magnesium between them. So it looks like, and this layer of boron, they are honeycomb. You can show again the top view. You see they're honeycomb. So it can be carbon here. It can be some graphite, or it can be some graphene. And the boron, it also creates these honeycomb forms. And we can and we can say that probably it's like boron in the form of graphite, which was intercalated by magnesium, but we don't have boron in the form of graphite. So that's interesting because boron and graphite, the carbon, they are too close in periodic table, but graphite creates these structures. But boron also creates them, but only with combination of some other atoms. So maybe, probably, magnesium connects these layers in some way. So because in absence of magnesium, we will not get such a good structure. So it was my few words about the structure.
Okay, so let's probably open this.
So you choose now you choose the structure. You use eyebrow 4 because it's hexagonal symmetry. Yeah. Hmm?
Huh? I can show you these ones.
PBSO, KGPAL, and PBSO, KGPAL. Magnesium and boron. And this is a folder in your computer, not in the.
That's
Oh, okay. It makes sense. So you
but I've also transferred it to the.
Yeah, I think it makes sense. So you will fill all the files on the computer and then transfer them to the cluster.
I'm actually already filling it on cluster.
Okay. So
just I don't know a way to directly download something from Telegram to cluster. There probably is something.
How to launch Telegram cluster? I think probably it's impossible. I don't know about this cluster, but really clusters about what people care. It's really hard to connect them to internet, to some open internet. So it's you had to, for example, in Dresden, you had to write few. You had to write few lines with some information about VPN to take something from internet.
This one is actually directly connected to the internet because I downloaded Conda directly from the website.
No, Conda is okay, but I mean about other programs. So other programs can be blocked.
Maybe okay.
You get Conda with we get with some so it is already secured all these channels.
Okay, so what's the next step? So yeah, let's see. So
Angstrom to Bohr, yeah. I also use this.
306, yeah, 306. So let's paste. And so
so now you transfer angstroms to Bohr because in quantum espresso we had to use Bohrs.
Yeah, so and then I divided vector C by vector A to get 1.15.0.
Yeah, because LDM3 it's vector C divided by vector A.
That's probably enough for 7. Yeah, that's because C LDM3 is defined by C.
Yes.
By 8. So number of atoms. So let's see. Coordinates. Oh, what we can do, we can export S, Oscar.
So you should to have the coordinates You follow? Do you follow it?
Yeah.
You should get the coordinates. Easiest way to get them it's from Postcar in materials project.
So here we have 3 atoms. So not 3, 2 types of atoms. ECAP VFC, what should we choose?
You can check the pseudo potentials and then take higher. In normal way, you should make convergence test, but I leave it for homework. The convergence test for Tainom
Here
tool
it's 58.
58, yeah.
And here it's 43, so
43.
68 probably.
60, I think maybe 70 is okay. 70 maybe is okay.
Okay. I don't really want to take forever, but okay. So atomic species.
It will not take forever. It will take half a minute on the cluster of this relaxation.
Okay, so magnesium, name of file.
Yeah, you have to specify atomic masses for magnesium, for boron.
Oh. So.
And it should be right after the name, atom names.
Yeah.
Before, so between pseudo potential and magnesium. So
okay,
you should.
Confused.
Oh, we have almost all. Yeah. We have system field, atomic species. Now we had to take atomic positions from Postcar.
We can just copy this. See.
Yeah, you should write the name of atoms.
So key points. Something like by 887.
88. Maybe 7 or maybe 888 will be also okay because it's
It's 115 probably 887.
Maybe 7. Yeah. Okay.
I think 7.
You can at first glance you can take the key points like so you can multiply cell DM1 on a key point, and if you get 40 or something, you can say that it's rather good key point number for some first shot. It's not some physical rule, but it's some just empirical rule.
Is it correct syntaxes?
I think that it's correct. Yeah.
0, 0, 0, 0.
It means that we start from gamma point.
Yeah. So now escape.
You can save it.
And
all of you follow this. So all of you.
Open it so you can copy.
Then you had to maybe it's you see between atomic positions, crystal and magnesium coordinates. You see some empty line. Maybe you should delete it.
This.
Yeah, I don't know if it will work with it. Probably work. Okay, but without it, it will work.
Put empty line here. Okay. Also, I learned how to go to the end of the file in Vim. So start of the file is G. Oh, no.
You should, yeah.
So it's G, and Shift G is the end of the file.
Shift G is the end of the file. Yeah, cool. It's really useful.
So how to copy something to Boston?
It's like you
go to file zero. So you have on the left is your local PC, on the right is cluster. So you navigate to the whatever folder you want to save, Then if you want to copy the whole folder, you
can just drag it.
I've done it this way, and right click and upload.
Okay, but to which folder in the actual cluster?
In folder what you want. You can if somebody uses this account before, you can create Igor folder, for example.
Now QScript.
Yeah, QScript is a new thing from last time, so we should use it to submit the works, the jobs onto the cluster.
I don't think we need to redact anything.
I think that it's okay. Yeah.
Yeah. So
because I use the script.
So
QSub.
QSub. It's
QSub.
What does it stand for?
Submission.
Maybe. Here we go.
You can check it. QStat. QStat by QStat. Use tail minus f. Tail minus f.
I don't think there is any. Oh no, there is.
A lot. Yes, a lot.
It started.
I think maybe it's already finished because it should. For me, it took like 30 seconds. And now we have the same system.
Job done?
idea. Yeah, you see, 43 seconds. So you have finished relaxation. Now you can take the structure, the new lattice parameters, relax it, and proceed with our calculations and use it for SCF. So Mikhailo, you can show
We
it.
can use Vim to not transfer any files from the cluster. So -b2. So if you press tab, it will automatically add everything. So
Automatically fill the name, yeah.
fill the name, so it fills. So we specify that we want out file for the two files in and out. And
yeah, now we take from output the relaxed parameters, relaxed lattice parameters.
So what do we the
atomic positions didn't change, so it was ideal from the start. But CLDM1 and CLDM3 changed, and you see they changed quite a lot.
I don't see them.
You can go up. Yes, and here you see it.
Oh yeah. So we copy this.
CLDM1 and CLDM3 changed because our structure have changed. Yeah, you can copy it, and maybe you can go slightly upper to show the. You see here. You see the stress kilobar. So now it's almost 0. So our crystal lattice it's almost in ideal state for this parameter. So there's almost 0 pressure, and now you can go to the up of the file and see this thing from the first.
From the first.
You will do it forever. Okay. Yeah, you should go by your lifehack G.
Yep.
And now you can go to the output of first SF cycle. More and more.
No.
Yes, here. Maybe slightly lower.
Yeah. Oh,
the furnace. Yeah, here. You see, it's it was after the first cycle. So when we took the structure, it was not in ideal state because you see on A and B vectors we have pressure 6 kilobars, which is rather big, and then for C we have the biggest -31 kilobars. So that's why it had to be changed, and it was changed in relaxation. And total force still zero, so it was ideal positions. Sometimes it happens that crystal structure have ideal positions that usually it's some super high symmetry Viper positions like this hexagonal structures. So what means that it's minus? It means that it was too high. So the distance between this the difference in c direction, it was too high and it should shrink. And it happened. So you see it was like 1.15 and in the end you got 1.12.
Mm-hmm.
So now you can fill SCF file.
So very important how to exit Vim.
How to exit Vim? Just
Yeah.
I use
so,
Control Z.
Yeah. No, the proper way is like it's not semicolon. How do you call it? It's
Q. Two dots.
Yeah,
Two dots, Q.
You enter and you exit Vim.
Now we are moving to, so we made this relaxation, we got the structure, the relaxed structure. Now we go to SCF and we should use this new structure to make SCF calculations. Yeah, maybe you can copy a lot from previous.
But we see was 17, yeah.
Mm-hmm. Here you see number of bands.
So
it's not very important for SCF number of bands, but it will be okay for our calculations.
So we need to
estimate it.
Yeah.
By pseudo potentials. So we should use pseudo potentials to estimate it.
Okay. Yeah, I remember. So magnesium, 2s. Don't remember this.
So here is like 10 electrons in magnesium.
10 electrons here and 3 electrons in 4. So by 2 it's 16, and add some. Like
16. So we should divide it by 2. And we get 8. Yes, 8. And we should take slightly more to use this conduction. You can take maybe 12 or maybe 20. So the more the best, maybe 20 is okay. So you will get more.
Okay, so
empty bands.
Okay, and the way to do it, so
and maybe you should copy all those things.
So W2 save. Oh,
yes, WQ.
Yeah.
You'll get what happens here. So we calculated, we inserted CLDM1 and 3 here, the new parameters, and all other things just almost the same.
You don't change it. No.
Yeah, you can take the same key points. All these atomic species, atomic positions, key points, you can just copy. It means it's almost the same. The most important thing from relaxation, it was CLDM1 and CLDM3.
No.
Yeah.
No, we also keep the key points.
It mean he meant the same number of points for relaxation. Yeah, it should be. It can be the same, it can be not the same. Doesn't matter.
So okay.
Usually, this system is too small. You see, 30 seconds to complete relaxations. But when it takes real hours of days, you should play with the key points. For example, I take a lower number of key points for relaxations and then higher for SCF, because from SCF it should get electronic density, at which we need a higher number of key points. And for relaxation, I take a lower number just to increase the speed. It's not very optimal. The best thing is when key points the same for relaxation and for SCF. It's the best thing, because then you can be sure that you take the structure with no pressure.
So, can we go?
Let's wait for all. Let's wait for Igor.
We can, for now, we can transfer pseudo potentials to the Benz folder. We will need it anyway. So
you had to copy pseudo potential. Now you can fill the Benz folder, yeah? You can copy here pseudo potentials. And also you had to copy XML file. Yes. So this file was generated during the calculation, and it has information about electron density and other. And you also had to copy MGB2 safe, this folder safe, because it contains the files with electronic density. It will take some time. Yeah, now you can start to fill Benz in file. Maybe we can. Now we are going to fill in the gaps in Benz in file.
So
usually it will be almost the same like in SCF. Yeah. And system will be the same.
no. So number of Benz was 1.
The only difference in key points.
3, 2, 7. Key points, yeah. So I don't remember what the difference.
In key points, you should specify the pass.
Oh yeah. So
you can copy all other information.
Yeah.
Which you need.
We need to copy CLDM.
CLDM, IBRAV, yeah, all these things.
So.
And then you should write using SIGPass. You should choose the pass. So I think all other things are okay. Except you should choose the KPass. KPass. And then in this KPass, we will build our key resolved DOS pass. Sig and destroy. SIGPass, yeah.
Pass. This.
Here you can open a save file or relax file. So it doesn't matter.
First of all, I need to copy it to.
Yeah, maybe you should copy it on some on desktop.
So.
You can refresh it. You can refresh this file, this folder in EFC.
Overwrite.
Interesting directory UA file, Ukrainian file.
Yeah, I don't see.
You can see here directory, file type, and UA file.
Yeah. It's pretty stupid. It just goes by the Android file.
So now we should to choose the key pass in Brilliant Zone, and we used SIGPass tool for it. And maybe Mikhail, you can show us the Brilliant Zone
Okay.
and explain how do you choose it.
So So this is the Brilliant Zone. The path it suggested is G gamma mk gamma. So we go here, here, and return, and then it's a l h a. So we just go to the top layer. I'm not sure how to call it, and
yeah. So
go
we
to the
use
same path.
so we use one closed contour in the middle of brilliant zone, then we go up and use the same in the up part of brilliant zone. And you can see here in the this is what I mentioned. You see this some pattern of graphite, yeah, this hexagonal things, and you see another cell. So it's like we have two cells. One is hexagonal cell with for like graphite hexagonal cell, so and other cell is just this trigonal cell for magnesium. So it's like if you want to see to look at it as interaction between two structures, magnesium and some hexagonal boron. But it's one structure. So it's magnesium B2. And now you can type first of all you should type the number of this letters of these points.
It's 8.
Yeah.
So then we just
Then you copy coordinates.
So we start from gamma.
Yeah. Then you type number of points between these key points. Number of key points. Yeah, but no, this is not very. You see, for after the coordinates, you should type number of key points between gamma and m. You should type, for example, 20. Yes. 20
yeah.
points. And then you should type some comment between gamma, because gamma is just comment. So it's not what a program use. It's just for us, for people. For feedbacks. Yes. This is pass before this. That's our pass. This is also part of pass, but we don't use it because we have to. If you want, I can show you some way how to do it, but now you can do it. M05.
Я скопіював просто з браузера. Цей символ.
Можете написати просто буквами гамма англійськими. Ну, це ж коментар для нас. Це все одно коментар для нас, як буде людей.
Так, можна просто гамма написати. А я думав наш.
It was feature. Yeah, you can copy it.
Вставити і переписати. Так.
You can copy it and then just change the C coordinates.
Yeah.
Because all these paths, they are different, only that they are shifted, translated to the edge of brilliant zone.
This is not gamma. This
no, it's A. Yeah.
That's
L, H, and also
A.
Yeah. So A is some opposite to gamma. It's the middle of edge. No, it's okay. It was okay. So looks like everything is great. You can save it. Have all of your folds. Maybe you can it can stay for a while. This suggested path not every time the path we need. Sometimes we need another path if we want to specify some. For example, we have some RPath measurements, and we want to see some different part of brilliant zone. That's why we should choose our own path. So it's not the optimal path in all situations. For this situation, it's okay because it's rather standard for hexagonal. Or maybe you can start the calculation if everybody had filled it.
Ну просто звідси скопіювати по порядку. І дописати коменти так, окей. So, let's check QA script. So, it is correct. It is DOS.
IDOS, yeah, you see, should it?
Proj VFCX.
Yeah, you PW.
Oh no,
It is-
that's the wrong script. With
You should-
KPDOS.
Yeah, you should change it.
It was not. I checked.
Bands and the name, also the name. Like bands. But then what should we also need as a script?
16 course or
It can be 16, it can be 8. If you used previously 16, it's better to use the same number of cores which you used in previous steps, because wave function is distributed. You see the 16 number of wave functions, so it's distributed.
Okay, so and let's start. Okay, so
Треба цього правила, і там, мабуть, вона ще захоче пару. Да. You see, yeah, 36, but how many, ладно, зараз, how You see, you can go up, more. How many components do we have here? How do you think? How many components do we have?
We've had 1 and 20, so it's something like 1, 2, 3, 140.
141. Yeah, 141 because we start from not from 0, but from first key point. Yeah, and you can so we had to calculate 141 key points, and you see we used pool. It's in our script, so we divided. Mikhailo used 16 processors. You used 8 processors, so the number of processors divided by this parameter and pool which we specify in our cluster, and it means that we calculate 4 key points at one time. For Mikhailo, it was 4 CPUs and each key point. For LC, it was 2 CPUs for each key point. And you can go down, and to the place where all these key points calculated. Some symmetries.
Oh, this?
No, even further down. Yeah, it's just the number of components. You see,
Oh, yeah.
141.
Yep.
Yeah, 141. And what slightly lower, I want to show you the dynamical run. So you used 16. No, yeah, you used 16 cores, and it estimated dynamical run 52 megabytes per process. And then it divided this 52 by 16. It means that every core had to choose 3 megabytes for 3 megabytes. It's really super tiny number of this RAM. And then you see calculations. You see computing key points 1 of 36, not from 141, but 1 of 36, because you should divide, because you used npool 4, that's why you should divide 141 by 4. You can do it and you get with some round 36.
With rounding up.
It's right, so it should 142 will be divided by 4, but it's like one set. So we have 35 point sets with 4 points and 36 points that will have 3 points, because
144 actually.
44. Okay, yeah, 44. So it's so the last set will have only 1 point, and that's this is one part of parallelization. When you just take this RAM, 52 megabytes, it's nothing. But if you will have 100 gigabytes, and it's really easy. It's like 80 atoms. For example, in my calculations, 80 atoms had to use 100 gigabytes, and then you divide it by maybe not 16, but maybe 32 processes, because each processor have a limited number of megabytes. And if you will start some calculation on only one core, and it requires 100 gigabytes, it will not start. That's why parallelization is very useful. It's first level of parallelization, when you divide it by the number of cores, and second level of parallelization, when you take these key points and you divide these key points by the number of cores. It also makes calculation faster. Yeah, that was all what I wanted to say about the sync. Now you can and now you can calculate this DOS.
DOS? Not Benz2?
You can calculate Benz2 if you want. And then we get band structure. Yeah, okay, let's start. You can calculate Benz2. And we will
Там ничего нема.
Appends.x, yeah. And you should change the name of files in script. So in file will be like Benz2, in out file Benz2 out.
Can we just directly call it from here?
No, because you had to upload some. You can you can try to do it. You should go to script. Okay, Lana, you can do it from here. You can do it only from the node. So you should go to script. You should copy this libraries which you should export. Then you should go to the node. Then in the node, it will take a lot of. It's easier really to to deal with script.
So our executable should be
Benz.x. Yes, you are right.
And let's see.
Benz, yeah, looks like everything okay.
Benz2?
Benz2, yeah. Benz.x, yeah, you should can. And it will take really some, maybe few seconds.
Meanwhile, we can redact our PDOS.
Yeah, just check if it finished. Because for PDOS, what do we need for PDOS? We need data from this file, from output. Yeah, it's 5 seconds.
Okay.
But it's really a huge file, 4,000 lines.
Yeah.
You should go to the app.
Oh, yeah.
You should go to the app, yeah.
Where?
By your hack, by G.
Yeah.
Because it will take forever. Yeah, but it's not very useful. So x equals, no, we don't need 0. Yes, this is the first key point, x1. So x1.
It's pain.
Трошки челендж, тому що Антона теж може там ругатися, робити щось і так далі.
У мене є
Ну, можна спробувати, наприклад.
ідеї, ну, що ти працював, я не чую.
Все готово, да?
Так?
So let's slightly discuss it.
You see that moreover, more or less, it's like titanium Selen 2. I think because it's these two structures, they hexagonal, they have more or less same crystal structure. It's like one metal and then some Selen or boron 2. And here from gamma to A, so when you in brilliant zone go up, you see that it's not this band. It's not like flat. In titanium Selen 2, it was almost flat, but it goes at some. But it also not so. Як це слово було? Steep.
Steep.
So
Через довгу і.
so it's not so steep. Yeah. It means that in our Fermi surface we'll see some silent cylinder, which will be not so wide here and wider here in A. And now we can place on the same. We can place on this band structure our DOS.
And it's the last part of today's calculation. You can also proceed to it. You can open that file. You can go to your cluster, because now you're on node. Yeah.
So
Exit. Yeah. And you can open that KP DOS in. KP DOS in, and I'll tell you a few words about it.
You see, it's also projected WFC like we used for partial doses. And some parts the same. For example, prefix, dir, fill PDOS, it means that we also calculate partial doses and we fill them in this file. But for this calculation, it's no need to use this partial doses because it's not partial doses for all brilliant zone. It's partial dose for just for some paths, and it's not too interesting. But we still have this file. Then we have different things. Carries over DOS. True. It means just it's by default it's false. It means that we just open this option, just switched on this option to calculate carries over DOS topic of our laboratory. The Gauss, it means this broadening of this file. It should be the same as for our file. And for our calculation files, it was like 005. So I keep it the same. Symmetry is some parameter which don't include symmetry. Now it's not so necessary. Field project. So it also make projections on orbitals in some different file. And delta is just resolution in energy. We can take it 0.0001 and we will get super huge files. Or we can get it rather normal, rather adequate 0.01 and to get adequate dose. So now you can start this calculation. You should change the script.
Yeah. So.
And we use project Proj WFC for calculation.
So the name is yeah. This?
Yeah, and name of that file. So you see that the script it's rather convenient. It's very simple. It may look some terrifying, but intimidating. But what we need is just few lines.
Proj VFC и назва файла.
Proj VFC because we want to create those.
Ищет.
You got a lot of files, and this is
our just old good files. You remember these files from partial DOS calculations, but now they are rather different. You can open what you can do. You can open this file pdos.pdos.tot. So it means that that's total. It will take some time because it's very huge.
Так, pdos dot, pdos tot.
Tot, да.
Yeah.
It will take some time because it's huge. This file is really huge. And you see what we see here. You can go up
It doesn't even show how many.
because
lines does it
it's
have?
really huge. You
1
see.
million.
You see 141 key points. Yeah, we had 145 exactly 145 key points, and now what it makes what this calculation makes, it takes each key point, each of this 141, yeah, and it built it built the path for each key point. So it takes this key point, and you see how many, yes, how much. So it take the whole path for this key point. So it's like 141 multiple on 141, and you should get the same as this number. You see, it's really crazy, yeah.
Yeah.
And you can go up. You can go up. You can go to the top. Yeah. You take for yeah. You see, the legend I key. It means a key point. No, just number. First key point, second in your path. Then for each key point, it takes the energy and takes the DOS, and it takes it for the whole path. So you have this. You have 141 1. Then you have 141 2, and so on. So you have lines like 141 multiplied on 141. So it's huge amount of lines. Yeah, and so for each key point, it created the whole I don't know how to say. So it created the whole picture of our path for each key point. Yeah, and then you can combine them. So here you have 141 plots. You can plot this. You can plot second, third, and so on. But with our script, we will have it's like quasi 3D script. You can combine all of them in some quasi 3D temperature diagram. You can go out from this file and then go to the script.
Okay, so
Script is keypdos total. mgb2 keypdos
okay.
total.
So
Yeah, you should. It was 2332 Fermi energy. Yeah, file because I used the script for myself.
Yeah.
Then you should you see here. You should go over. It's like you remember it was x1, x2, and x3. It was some coordinates in Brilliant zone, but now we have some just number of key points, and it means that 21. Yeah, it means that it go to that huge file and it take 21 this points 21 multiplied 141, and then it creates our first M point, and then it goes to second. And here you see 141. Now it's some functions. You can be maybe at home more familiar with it. It's some function to plot this case over DOS. You see, it's core map, and it's almost the same which we used for partial DOS, but with some upgrade of the function. Yeah, and here we have not two. When we calculated partial DOS, there was two coordinates. It was DOS and energy and DOS. And here we have three coordinates. So we have key point, energy and DOS.
Yeah.
And we should combine them on one plot. And DOS, the third thing, we will show with color.
That's okay. So as you said,
You can, yeah, you should go to the node.
yeah. So
And Python
3.6.
no, without band.
And it's called MGP2.
I hope it will work. For me, it worked.
Takes some time.
Yeah, it takes some time because it's a really huge file.
Okay.
And sometimes this file is so huge that you have to use some tricks in Python to deal with it.
Oh, yeah.
I saw some tricks like you had to zip it and then to read by step by step.
Let's open it.
Hope it works.
The resolution is not particularly.
Why it's not so good resolution? Yeah, because we used only 20 points between this. If you will use 100, you will have two huge file, but it will be not one. Okay, if you will maybe 30 or 40 will be enough, but the file will be. But with, even with such port, you can.
What?
Да. So you see, and the other thing, the other difference, that distance between these points is the same. Is the same because the distance is like 20 points. If you want, the distance will be in the same proportions as you have to take the coordinates in the Brilliant zone and take the number of key points according to, for example, if this is twice bigger than this, you should take here, for example, 40 points and here 20. So you should play with it. But it's not our goal was to get the ideal plot. Maybe if you will calculate it some time for some article, you have to do it. But now we have to see just things what happens with our DOS, and we see that the biggest number of DOSes is here in the which is rather logical. Yeah, so it's and now I propose you to do next thing. You can go to the script, Mikhail. You can go to the script, not to the script, but key points, key PDOS in. Key PDOS in.
Exit.
Maybe you could. Oh, okay, ладно. Нормально. Keep it DOS in. And here you can change it from 0.05 to 0.2. And you will see what will be changed. To 0.2. Yeah. Then go to Python script.
But we haven't recalculated anything.
Huh?
We haven't recalculated anything. We just changed the file.
To Python script, I want you to change the name of file.
We just change.
I want you to have two files, not replace it by two files. So you have to change the name of file.
Okay, Python script.
I want to show you what will happen if you will change that thing, the Gauss. Maybe it will work. So I didn't do it by myself. So maybe nothing will change. So it should change, but maybe we have to do all the procedure from the start to see the difference.
Script.
Yeah, you should go to the end and just change the name of this file because in this case it will be replaced to okay, and then we will see this difference. Now you should to recalculate it. So Q sub, Q yeah. I hope it will work. What's your guess what will happen if we
increased the Gauss. Yes, they should become broader. Okay, I say maybe it will work for maybe some okay, maybe it's not the best idea to recreate in the same folder. Maybe we need second folder for results don't interfere, but maybe it will be good. You see that it has total charge 2.4 on p orbital, and all other orbitals like 1 and 1, 2 on 1, 1 on 1. Is that px? It finished, but Mikhail is not here. You can try to do it by yourself. You can show, Mikhail, you can show previous. So this is with the Gauss 0.005 reapers. So it's lower broadening of the spot. And now you can go to the next. And we see when we increased it 4 times, it became more broadening. So that's what makes the Gauss. I explained you this mythical parameter, the Gauss, and now you see what it makes. So it broadens this our lines, and it became more like some ARPAS calculations. So what happens if we will create? Okay, start from the first picture. So just for the history. Okay. You may start from the bands from from here. So this is just bands we have created with our usable routine. You see just lines, and this lines shows energetical bands of items. Then you move to another picture, and here you used the Gauss. So you used not so huge broadening to it, and you see that it's even dotted because we don't have so much dots. We have only 20 dots between it. But we see that we have a lot of states here and some states here and not so huge states here. So then you move to another. Then we increase from 0.005 Rydberg to 0.02 Rydberg the Gauss, and we see that it's broadening. So here our main part of electron states, and here we see not so huge amount of electrons. And now we made we increased the Gauss really huge here, a few electron volts, and you can show it. Yeah, it's 0.2. The Gauss, it means that the broadening is like half electron volts, so it's like maybe 2 electron volts. So it's huge here. It's half electron volts, and you see that we can say nothing about. We can say just the electrons somewhere here. It's some parts maybe of this some parts of these lines, because they was really so this line goes like this. Yeah,
this line, something like this line.
We see that it just exists there. Yeah, that something exists here, but maybe it's closer to experiment. And the next thing what I want you to show is the last thing. The particle atoms. You should go to the to Node, /R29. Go to this it's better to do it with some adequate the Gauss. I mean you should change the Gauss before and recalculate.
Yeah. Okay.
Change it to 0.02. 0.02. Wait. Or maybe 0.01. Let it be 0.01. Yeah. This is the Gauss. Then make the calculation, and then we will do the same, but for
the structure, the whole structure, and for different atoms. For magnesium and B, it will be very fast, but it will be very interesting what we will get. Ну, ще раз наш відео, я не знаю.
Ага.
Бачите,
Так.
що сталося? Це що у вас?
Це марган.
Це магній, да?
Магній.
Тобто магній виходить, він в основному тут
Да.
деталі магнія, типу
Так.
згори накидав.
А тут маленькі.
І тут трохи. Насправді воно тут десь теж є, просто його не дуже видно. Давайте тепер ще бор.
А бор?
А бор все інше. Бачите, що воно пише?
Це
Це є
основне?
конструктор. Да, це виходить конструктор. Причому вони можуть, от, наприклад, ця зона, да? От я пальці тримаю,
Ага.
перейдіть назад на магній.
Ага.
Бачите, вона лишилась. Тобто вона спільна для магнія і для бора, оця зона.
Ага.
От. А виходить, що бор в основному дає от всі ці цікаві ефекти.
Угу. Цікаво.
Ну все, також можна і орбіталі теж рахувати. Тобто, якщо ви захочете
Ага.
орбіталі,
СП.
Тобто ви реально можете його як зробити як конструктор, дивитись просто, як із чого воно складається, цей графік.
Мгм.
Тобто це дуже класна штука.
Так.
Все, можемо вже виключати. Дякую вам. Потім ви прямо тягли, тащили. 2 хвилини лишається.
Мгм.